December 1944. Inside a dimly lit hangar on the outskirts of Rechlin, the air smelled of oil metal and defeat. Germany was still fighting, but every man in that room already sensed the outcome. Under the glare of a single floodlight stood a massive engine crate marked in fading stencils, Pratt and Whitney aircraft, R-2800. It had been salvaged from the wreck of an American P-47 Thunderbolt shot down over northern France. The fuselage was twisted and burned, but the engine, this enormous round 18-cylinder beast, had somehow survived intact. Technicians from the Luftwaffe's experimental division gathered around it like priests about to open a relic. They whispered among themselves. "So, this is what powers their flying milk bottles," one muttered, using the mocking nickname German pilots had given to the P-47s. To them, the American fighter was a brute-heavy, clumsy machine that defied every principle of elegant engineering. No one understood how it could climb so high, take so much punishment, and still come home. The Luftwaffe wanted answers. The order from Berlin was clear: disassemble the captured engine, analyze every component, find the secret. The crate was pried open with crowbars. The mechanic stepped back as the light hit the metal 1,200 pounds of alloy and power. The double-row cylinders formed a perfect circle, gleaming under a layer of grime. A junior engineer named Otto Henschel ran his hand across the casing, tracing the embossed words, "Double Wasp." He had repaired hundreds of BMW 801s, the engine that powered Germany's own FW-190s, but this thing looked alien. The cooling fins were thicker, the bolts oddly oversized, the exhaust manifold, arranged in a pattern none of them recognized. "Too heavy," someone said dismissively. "The Americans overbuild everything." Henschel didn't reply. He had heard that before. He also knew that overbuilt sometimes meant built to last. For a moment the hangar was silent except for the clink of wrenches and the hiss of kerosene lamps. Outside, snow drifted across the airfield, muffling the distant sound of artillery from the Western Front. Inside, the Germans began the slow ritual of dismantling a masterpiece they didn't yet understand. As the cowling came off, a sweet metallic scent filled the room. The first cylinder head revealed a precision of machining that made even the senior engineer pause. The threads were cut so finely that they seemed polished by light itself. There was no chatter, no tool marks, no imperfections. These were not parts made by hand. They were made by an industrial civilization operating at a scale Germany could no longer imagine. In that moment, the tone in the hangar changed. The jokes faded. The laughter stopped. Henschel realized what he was seeing was not just a piece of machinery, but the physical embodiment of America's industrial might. Every surface told a story of mass production perfected, of factories running day and night, without fear of bombing, of supply lines that stretched across oceans. He understood that each P-47 engine rolling off an assembly line in Connecticut came from a nation that could afford to build 1,000 more. When they finally rotated the engine to expose the rear section, a murmur rippled through the team. A massive turbine housing sat behind the crankcase, larger than any supercharger they had ever seen. Henschel leaned closer, following the maze of stainless steel ducts feeding into the intake manifold. "It's not a simple supercharger," he whispered. "It's a turbocharger, driven by exhaust gas." The chief engineer frowned. That was impossible. Turbocharging required heat-resistant alloys Germany didn't possess. Nickel, chromium, cobalt, all of them rationed, all of them scarce. Yet here it was, humming silently in captured glory. The older men exchanged uneasy glances. They had spent years perfecting engines like the BMW 801 and Daimler-Benz 605, tuning them for power and efficiency. But this was brute strength forged through abundance. It wasn't beautiful, it wasn't clever, it was unstoppable. Outside the hangar, the wind howled across frozen runways. Inside, under the flickering lamps, a German mechanic stared at a machine that shouldn't have been possible and realized something that few dared to say aloud: the war had already been decided long before the first shot was fired. Not by aces in the sky, but by men in factories who could turn steel into miracles faster than an empire could understand them. If you believe wars are won by brave pilots, type 1 in the comments. If you think they're won by better machines, hit like. And if you want to uncover the next secret buried in history, subscribe now, because this story is only beginning. In the winter of 1944, the Luftwaffe's Technical Bureau was drowning in bad news. Squadrons once filled with veterans were now led by boys barely old enough to shave. Fuel stocks were rationed to the point that training flights had been reduced to 30 minutes a week. And yet, from the Western Front to the skies over Berlin, a strange, new American fighter kept appearing, bigger, heavier, louder than anything the Germans had ever seen. The men in the intelligence office at Adlershof called it the Thunderbolt. Reports from pilots sounded exaggerated, even absurd. We hit it dozens of times, one transmission read, and it kept flying. Another claimed a P-47 had dived straight through a formation of FW-190s, its guns roaring, and vanished into the clouds before anyone could react. At first, the High Command dismissed these accounts as excuses. No airplane that size could fight like that. But then the wreckage started arriving. Crashed Thunderbolts were being recovered across occupied Europe, and the more they examined them, the less sense they made. Their engines were enormous, their fuselages built like armored vaults. Even a single machine gun burst that would have torn through a Messerschmitt barely left scratches on the Americans. Luftwaffe pilots who once mocked the flying milk bottle began to curse its name. One veteran from Jagerschwader, 26, the elite Schlageter wing, summed it up bitterly. They fly like anvils, and they fall on us the same way. What truly alarmed German engineers wasn't just the Thunderbolt's toughness, but its altitude. On the Eastern Front, the Luftwaffe had dominated with the FW-190A, a low to medium altitude dogfighter. But over Western Europe, P-47s were climbing beyond 30,000 feet, well above the operational ceiling of most German interceptors, and attacking from above with devastating speed. The culprit was the engine, the Pratt and Whitney R-2800 double Wasp. At altitude, where air was thin and temperatures could freeze metal solid, this engine somehow maintained full power. The BMW 801, by comparison, gasped for breath above 25,000 feet, its mechanical supercharger unable to feed enough air to the cylinders. The Luftwaffe's technical office launched a formal investigation. They needed to know how the Americans had done it. Orders were sent to the Rechlin Test Center to acquire and dissect any intact R-2800 engine recovered from wreckage. The hope was simple: find its secrets, copy them, and restore parity to the skies. But by then, Germany's industrial reality was collapsing. Allied bombers had leveled ball-bearing factories in Schweinfurt, aluminum plants in Norway, and fuel refineries in Ploiești. Even if they discovered the secret replicating, it was another matter entirely. Still, the investigation proceeded. Pride demanded it. To understand what made the Americans different, one must understand how the Germans thought about machines. To the engineers of Daimler-Benz and BMW, an aircraft engine was a masterpiece, a creation, to be tuned, polished, and improved by craftsmen who believed beauty and precision were inseparable. Each component was hand-fitted, each bearing inspected by eye. The result was performance unmatched in the world when the materials were pure and the hand steady. But it was a system built for perfection, not for war. In America, the philosophy was the opposite. The R-2800 wasn't designed for artisans, it was designed for assembly lines. Every bolt, every thread, every gasket was standardized so that thousands of factories across the country could build the same engine with identical tolerances. Instead of handcrafting, they used machines so precise that the difference between two pistons was measured in microns. Where Germany built art, America built quantity, and quantity, in the harsh mathematics of war, eventually becomes quality. By early 1944, this difference had turned into a strategic chasm. German pilots were fighting on two fronts with engines that required hours of maintenance after each sortie. American engines, by contrast, could fly dozens of missions with minimal servicing. A single factory in Connecticut produced more R-2800s in a month than Germany could build high-performance engines in a season. For the Luftwaffe, the captured P-47 engine wasn't just a technical curiosity, it was a question of survival. If they could understand how this massive machine worked, perhaps they could find a way to counter it. That was why, when the wreck of a Thunderbolt fell near Caen and its engine was found largely intact, it was shipped across Europe under heavy guard. The crate that arrived at Rechlin in December was more than just scrap metal. It was a symbol of everything Germany was losing: altitude, speed, and time. In a report to the Ministry of Armaments, a senior engineer wrote, "We believe the Americans have solved the altitude problem through wasteful use of materials and fuel." He meant it as criticism, but the truth was darker. The Americans could afford to be wasteful. They had more aluminum, more fuel, more factories, and more men. The Thunderbolt was not a miracle of engineering. It was the logical result of an economy that dwarfed its enemy. Still, the Germans couldn't resist one final act of defiance. They would open the engine, study it, and prove that they could understand even if they couldn't replicate. Henschel and his team were selected for the job because they knew radial engines better than anyone in the division. When the crate arrived, they treated it not as a trophy, but as a challenge to their pride. Before the first bolt was turned, the chief engineer gave a short speech. "Gentlemen, this engine is not magic. It is metal and mathematics, and both can be conquered." The men nodded. None of them knew that within hours their certainty would begin to crumble. What they would find inside the double Wasp wasn't just superior engineering, it was an entire philosophy of war, made tangible, one that valued reliability over elegance and production over perfection. If you believe victory comes from genius design, press 1 in the comments. If you believe it comes from relentless production, hit like. And stay tuned, because what they found inside that engine would change everything they thought they knew about power, altitude, and the limits of human engineering. The hangar was silent except for the sound of tools. Each turn of a wrench echoed like a heartbeat. Otto Henschel crouched beside the massive R-2800, his gloved fingers tracing the bolts that held the cowling in place. The Americans had designed this engine like a fortress. Every joint was sealed, every connection reinforced. When the first layer of metal finally came free, a hiss of stale oil and burned residue escaped into the air, a ghost of its last flight over France. The men leaned closer. Under the floodlights, the engine's anatomy gleamed like sculpture. To a German mechanic's eye, the construction was bewildering. The BMW 801 that powered the FW190 was compact, dense, and elegant, a triumph of efficiency. This American engine was its opposite: oversized cylinders, thick walls, heavy clamps, redundant systems. "It's absurd," muttered one technician. "They've built it as if weight doesn't matter." He wasn't wrong. The R-2800 weighed nearly a ton, almost twice as much as the BMW engine. But Henschel was beginning to sense something the others hadn't yet seen. The parts didn't just look heavy, they looked unbreakable. He removed one of the cylinder heads and stared at the valve assembly. The machining was immaculate. Every thread was perfect. Each gasket fit so tightly that it seemed fused to the metal. He called over the chief engineer. Together they examined the finish under a magnifying glass. There were no burrs, no imperfections, no tool chatter. It was the kind of precision one would expect from a watchmaker, not from an engine built by the tens of thousands. "Look at the uniformity," Henschel whispered. Every component could be swapped between engines, and it would still fit. That was the first revelation. German engines were hand-fitted, tuned by skilled craftsmen who adjusted parts until they worked together. Each one was unique. This American engine was different. It was interchangeable, a product of exact tolerances and machine perfection. Henschel realized that behind this engine wasn't just engineering skill, but a production philosophy his country had never mastered. Then came the second revelation. As they dismantled the rear housing, they uncovered a massive circular assembly unlike anything they had ever seen. The chief engineer frowned. "This can't be right," he murmured. The component was a turbine-huge complex and connected to the exhaust ports by a web of polished steel ducts. When the Americans said turbo supercharger, the Germans had imagined a small mechanical compressor. This was something else entirely, a gas-driven turbine harnessing waste heat from the exhaust to force more air into the cylinders. Henschel removed the casing carefully. Inside, a wheel of blades glittered under the lamplight. He touched the metal and drew his hand back immediately. The alloy was strange, smooth, hard, and faintly iridescent. They tested it with a file. The teeth barely scratched the surface. One of the metallurgists whispered, "This is not steel." He was right. It was Inconel, a nickel-chromium alloy that could survive temperatures above 700 degrees Celsius without deforming. Germany had experimented with similar metals, but never on this scale. Nickel was scarce. Chromium was reserved for armor plating. The Americans had built entire engines out of it. The realization spread slowly through the group. The reason the Thunderbolt could climb to 30,000 feet wasn't magic. It was metallurgy. The R-2800's turbo system allowed it to maintain sea-level power even where the air was thin as mountain frost. The turbo's exhaust piping alone stretched more than 15 feet, routed through ducts that circled the engine like veins. The Germans could see the logic, but not the practicality. To build one of these, the chief engineer said quietly, "We would need half the resources of the Reich." They moved on to the cooling system. Here, too, the Americans had done something different. Instead of relying solely on airflow across the cylinders, they had built a labyrinth of baffles, oil lines, and intercoolers that distributed heat evenly across the entire engine. It was crude in appearance, but brilliant in effect. The BMW 801 required constant monitoring to avoid overheating. The R-2800 could run at full power for hours without burning a valve. As the night wore on, the hangar filled with the smell of hot oil and sweat. Henschel's hands were black with grease, but his mind was racing. Every component he removed told the same story: redundancy, strength, and reliability. This engine wasn't designed for aces or one-off prototypes. It was designed for war, real war, where machines had to survive mud, cold salt, and inexperience. The Americans had built a weapon that could be flown by anyone, repaired anywhere, and mass-produced without compromise. When they opened the magneto housing, Henschel discovered yet another surprise. The ignition system was double redundant. 2 spark plugs per cylinder, 2 complete magnetos, twin distributors. If one system failed, the other would keep the engine running. In the Luftwaffe, such redundancy was considered unnecessary weight. Here it was standard practice. "They build like they don't care about limits," a mechanic muttered. "They don't have to," another replied. At 2 in the morning, they rolled the turbine wheel under the light and measured its dimensions. The chief engineer calculated the rotational speed over 20,000 revolutions per minute. His pencil stopped halfway down the page. "At these stresses, it should explode," he said. "Unless—" Henschel finished the thought for him. "Unless they know exactly how far they can push the metal." The phrase hung in the air, half admiration, half despair. By dawn, the R-2800 lay disassembled across 4 workbenches, its guts exposed like the anatomy of some extinct creature. The Germans gathered around the pieces in silence. For years they had believed in their own superiority, better pilots, better tactics, better technology. But what they saw on those tables forced them to confront another truth. The Americans had mastered something more powerful than innovation. They had mastered scale. Every component of the R-2800 told them that behind each Thunderbolt stood not a single engineer, but an army of machines workers and factories, an industrial ecosystem built to outlast any enemy. Henschel picked up one of the pistons and held it to the light. The alloy was flawless, the surface polished like glass. He turned it over in his palm, feeling its weight. In another life, it could have been art. He thought about the pilots who had flown this engine, the young Americans who took to the air, knowing that somewhere back home, 1,000 more engines waited to replace theirs. That was a luxury no German pilot could imagine. He set the piston down carefully and spoke in a voice barely above a whisper. "We can copy the shape," he said, "but not the soul." No one disagreed. Outside, the gray light of morning spilled through the hangar doors. The war was still raging, but in that cold silence, the men around the table understood what the front lines had not yet realized. The outcome was already written in metal. If you think victory belongs to those who innovate, press 1 in the comments. If you believe it belongs to those who build without limits, hit like. And subscribe, because the story of what happened after that morning would reveal how a single engine changed the course of the air war forever. By the time the sun rose over Rechlin, the men in the hangar were still staring at the rows of disassembled components spread out on the tables. The R-2800 had been opened, measured, and studied, but the feeling it left behind wasn't triumph. It was quiet awe mixed with something colder resignation. They had expected clever trick secret patents, perhaps a new alloy or a hidden valve design. What they found instead was something far more intimidating, the sheer perfection of repetition. Every part from the smallest bolt to the largest turbine blade was marked with serial codes that traced back to factories across the United States. Henschel held one in his hand, a connecting rod stamped with a neat set of numbers and letters, East Hartford, 1943, Lot 128. To him it was both a signature and a taunt. Each marking told the same story. This was not the product of a single genius or workshop. It was the output of a vast machine, an industrial organism that stretched from Detroit to Connecticut to Los Angeles. Later that week, a detailed report from the Luftwaffe's technical division arrived from Berlin. It included a set of statistics captured through intelligence channels. Henschel read them in silence. The United States was producing more than 850 aircraft engines per week, each tested, crated, and shipped across the Atlantic. Over 15,000 Thunderbolts had already rolled off assembly lines by that winter, and more were coming, Corsairs, Hellcats, Marauders, all using the same R-2800 heart. Germany, by contrast, was struggling to build 200 fighter engines a month, most of them assembled in underground factories, bombed so often that the workers had to finish parts by candlelight. To an engineer, numbers tell their own kind of story. They are the language of possibility and of doom. When Henschel compared the figures, he realized that even if Germany somehow duplicated the R-2800 exactly, they could never match the speed or scale at which America built them. The Americans had made precision into a process. Germany had made it an art. One could be multiplied 1,000 times. The other could not. Inside the hangar, Henschel began to disassemble the turbo housing for metallurgical samples. The lab analysis confirmed his suspicions. The turbine blades contained 22% nickel and 14% chromium metals Germany no longer possessed in quantity. In 1943, the Reich's stockpiles of nickel had fallen below half of what was needed for aircraft production. Chromium came mostly from mines in the Balkans now, under Allied control. Even if they had the blueprints, the materials themselves were beyond reach. A metallurgist handed Henschel the analysis sheet. "If we tried to cast this alloy with our current supply," he said quietly, "it would shatter before it ever reached operating temperature." Henschel nodded. "Then it isn't just the engine we can't copy," he said. "It's the civilization that built it." Across the Atlantic, that civilization was operating at full throttle. In East Hartford, the Pratt and Whitney plant ran 24 hours a day. Workers rotated in 3 shifts, producing 2,000 engines a month, each identical to the last. At night, the factory glowed like a furnace, powered by electricity, drawn from rivers and coal reserves, untouched by